So for this learning module, we wanted to look at how to simplify a system of forces and couples acting upon a body to a more simplistic representation. Now, the key idea behind this is if you have some body that you're trying to analyze its motion, and there's a bunch of different forces and a bunch of different couples which are tending to translate and rotate this body. It might be good if, for example, from a statics point of view, your responsibility is designing support structures that would keep it stationary. To be able to describe the aggregate or total effect of all those forces and couples by a single measure of how likely that body is to be translated and how likely it is to be rotated, or a single force and a single couple. That would be very beneficial from kind of a design point of view if you're designing support structures. And we'll see that a lot more as we get later on in the class. The one thing that I want to mention, and we'll kind of see this a little bit in the next slide, is although the big complicated system of forces and couples may have the same tendency to reduce motion from an external perspective, if you're kind of a viewer looking on from the side, it's not surprising that when you change the actual positioning of the forces acting upon the object, that the internal stresses and strains within that body are going to be different under the two scenarios. So even if both loading scenarios create the same external motion, internally they will have different effects on the body. So just to kind of see that, if we focus on the first row, we notice that this individual is holding a rod and there's a force applied at F. If that force were to be applied instead of at A, I should have said A, not F, but at B, then from his point of view, the reaction that he has to apply to keep it in equilibrium is the same. He's just got to pull back to the left by an equal and opposite force in order to keep that rod in equilibrium. Now, clearly, the internal forces or how much tension is in that rod is going to differ in these two situations. But from the perspective of an external observer, like this individual holding the rod, it's the same thing. I just got to pull back to the left by F. So that's why your book refers to this kind of situation of the force being a sliding vector. However, if we look in the second row, if instead of that force being applied along the axis of the rod, it were to be perpendicular to the rod and pushing it down, clearly the situation on the left is different on the situation on the right if we didn't have the moment there, the couple. And of course, the couple is one particular type of a moment. And the reason being, when the force is applied at some distance d away from the hand, he has to do a lot in his wrist to keep that thing to rotating, because that a force applied at a perpendicular distance d is going to tend to induce a lot of rotation. So if we were to come up with an equivalent internal representation of sliding that force down towards the hand, we would have to add in the effect that when we moved it in, the rotational tendency went away. So that's what that couple is doing. And I will actually show you, because I think the book doesn't do the best job explaining this. So let me just draw something really quickly. And of course, the image mate is not going to be behaving, and I'm not going to be deterred by that. I will just open it up again, and I'll draw it once the image mate starts. So this is a slide actually from the book, and it kind of makes this more complicated than it needs to be. What you see is you have this messy system of forces and couples acting upon a body. If you were to want to describe it by an equivalent force couple system acting on the body at point O, you could. And the big ideal is the resultant force would just be the sum of all the forces that are acting on the body. And that's just to say that when you move those forces to a common point, their translational effect really doesn't change. What really changes when you move them is their tendency to rotate the body. And the way that you account for that is this first summation term for the resulting couple is just the sum of all external couples acting on the body. This summation of all couples computed about the point O is related to the fact that when you move those forces, you have to account for the changes in the underlying tendency to induce rotation. And I think my .cam is back, so let me go back and show you what that means. If you have a rod, go back to that example we did earlier, and there's a downward force acting upon it. Remember that I can replace that from a modeling point of view as this situation, right? And the reason these two are equivalent is in this latter case, I just added an equal and opposite force up and down, right? Those cancel each other out. However, if I view these as a couple, which they are, I can replace these by a couple. And then what I've effectively done is I've moved this force down to the origin, and I've accounted for the difference in the tendency to induce rotation by this couple. So that's really what that equation is showing you there and what it's doing. So the key point that the book tries to make here is if it becomes a two-dimensional problem, it's just simpler because you're working with scalars. And we'll look at a two-dimensional problem here in a minute. One thing to keep in mind, you can always reduce any complex systems of forces and couples acting on a body to a single force couple system at a particular point. However, in certain cases, you can go even further. You can reduce the entire effect by that of a single force. And we're going to look at an example of one of these as well in a moment. The key point being is those special cases are when the forces are concurrent. If you remember, that was our static subparticle case. That's why we could kind of ignore rotation, as I hit on a lot when we were in that chapter. Also coplanar, meaning in any 2D problems we'll be able to do this. Also in 3 dimensions, if the systems of forces is parallel, we can replace their effect by a single equivalent force. So this kind of sounds confusing until you actually see how simple it is. So let me try to prove that to you now. So let's do an example problem. So I'm going to scratch that out just so we don't get confused either. So if you notice, what we were asked to do here is to find the equivalent force coupled system acting at A along with the single equivalent force location measured from A. And that's the wording. If you don't know what they're talking about, just sounds like it's incredibly complicated. What they're basically saying is if you have this rod here and you have these 3 forces acting upon it, could you come up with, from the tendency of these forces to induce translation and rotation of this rod, a single force and couple applied to A that would be the same? Well, if you just think about it, or you use those formulas from the book, either way, since this is a coplanar 2-dimensional case, we know that the equivalent force couple system at A would be this, right? It's the x component of the equivalent force couple system is just going to be the sum of all the x components in this diagram, and we can decompose these forces. I'm not going to show a lot of detail here due to time, but if you notice, that's opposite of the 30-degree angle, so this is going to be 50 sine of 30, and this is going to be 50 cos 30, and those are both in the positive x and y direction by our usual convention. In contrast, I can decompose this into 2 forces where if we think about this equivalent 3, 4, 5 triangle, the adjacent side, which is going to be 4/5 of whatever this magnitude is in the negative y direction. So this is going to be negative 100 times 4/5. And hopefully everyone is kind of getting down why this decomposition techniques, why it's so important to be able to do them relatively quickly. This is in the positive direction. It is opposite that angle. That angle in the equivalent triangle is 3/5 of 100, so that would be 60 pounds. So if I just go through and I add the horizontal components of these forces, no horizontal there, I have 60 pounds here, I have 50 sine of 30 there. So this is going to be 60 plus 50 sine of 30. If I do the same thing in the y direction, I have plus 200 there. I have 50 cosine 30 from the 50-pound force, and I have minus 80 from the 100-pound force. So rather than have to remember what the cosine and sine of 30 are, let's just do that. The first one we get, so let's just write, in case we need this later, which we will, 85 and sorry, that shouldn't have been 85. We want just the component there. 5. And then in terms of the cos d, that would be 43.3. So the equivalent x force is 85, and the equivalent y would be 200 plus 50 times cos d. I know I just computed that, but I want to keep the full precision in my calculation. It would be plus 163.3. So the next thing that I have to do after I've determined the equivalent force, that would be, so the ideal is that the equivalent force of these 3 forces, which would also be the equivalent of force applied at point A, is going to be 85 x component, 163.3 y component. Now let's find the equivalent moment or couple about point A, because remember, they technically are couples. They're free vectors, which is why we can move them. So in order to replace this 200-pound force applied 3 foot away from A by a couple applied directly at point A, what I would need to do is compute the moment of this 200-pound force about point A. So I'm just going to say it's the moment of the 200-pound force plus, now watch this next notation that I'm going to use relatively carefully. when I consider the moment of the 50-pound force, technically it's the aggregate moment of that force. But the x component, is it going to tend to rotate the body about point A? No, its line of action goes directly through A. So the only thing that's inducing rotation about point A is the y component of this force. So that's why I'm going to say plus m50y. And in a similar idea, when I talk about the 100-pound force, only the y component of it will be exerting a moment about point A as well. So in terms of determining the moment of the 200-pound force, this is an example where I can do the scalar approach pretty easily because I have that perpendicular distance. So if you think about pinning at A and pushing up, you'll notice that the 200-pound force is going to exert a counterclockwise rotation, and that's our positive, and that will be 200 times 3 in the positive direction. Same ideal, if I consider the effect of the y component of the 50-pound force, it's a counterclockwise rotation as well. So it is going to be 50 cos 30, which we had rounded, but since we're going to need a calculator again, let's just leave it like that. And how far is that perpendicular distance? 3 plus 3 plus 3 is 9 feet. So these are all in foot-pounds. We'll just keep a note there. And in terms of the 100-pound force, its y component, you can leave in the sign, but I think an easier way to do it is just say it's going to be an 80-pound force that if I pin at A is going to induce clockwise rotation. So that's a minus. And the magnitude of the force is 80, and the perpendicular distance is 6. So let's actually just determine what that is really quick. It's going to be 600 plus 50 times cos B, 30 times 9, and then minus 80 times 6. And just so I don't confuse anyone that's watching, that was 200 times 3. So it's magnitude of force times perpendicular distance. Magnitude of force times perpendicular distance. The signs are all chosen intentionally in order to have the counterclockwise inducing forces be positive and vice versa. So that comes out to be 509.7 pounds. And I should say foot-pounds, right? Since it is a couple. So I can go back here, and usually, like if you're entering this in your textbook, what they'll say is that the equivalent force coupled system at A is FR is 85 and 163.3, and that's pounds, and MA is going to be 509.7 foot-pounds in the counterclockwise direction. So you can just put something like that if you want. So oftentimes just know they will express this in polar form. So I'm going to show you why and how they do that in a minute. If I wanted to express it in polar form, I would just take the square root of the squares of each component. And that turns out to be 184.1, just a 3/6 figs, we'll call it 184. And in terms of describing its angle in 2 dimensions, I would take the inverse tangent of the y component divided by the x component, which would be, and helps to spell it right, tan d. That's my brain was getting ahead of me. That's why I was using the 2-dimensional arctangent function, which in MATLAB you enter the y and x components different. It deals with being able to unambiguously resolve inverse tangents in the second and third quadrant. You don't need to worry about it for our class. Mechanical engineers just usually draw it and actually show it directly. But that turns out to be at a 62.5 degree angle with respect to the horizontal. So let me go back to my dot cam and just show you what's going on here. Having all of these forces acting on the body is the same as applying a 184-pound force directly at point A, which is directed 62.5 degrees from the horizontal, along with a couple which has a magnitude of 509.7 foot-pounds. Now, if you think back to that's the solution for part A. If you think about what was said for part B, we were asked if we could take and replace this force coupled system at point A by a single force. So if you think about it here, if I were to take this force and view it in terms of its x and y components, if I slide this point of application out to the right, what's going to happen is this vertical component of the force is going to induce a rotation. So if I were to move this again, is what I'm trying to say. So now I moved it to point A. If I were to move it here, I would have to account for the fact that there's going to be moving it out from here would have an additional rotation associated with it. So what the book is basically asking for these types of questions is, could you move this force out to a point such that the rotation about point A would be equivalent to this moment? So for part B, all that you have to do, and if you remember, it relates to the y component, right? We need to find D, which is basically going to be measured from A, such that the y component of the resultant force times D equals the magnitude of that couple that we just computed. So in this case, D will be nothing more than the magnitude of the couple, which is 509.7 foot-pounds, divided by the y component of that force, which we determined to be 163.3 pounds. So if you see those units of pounds will cancel. And if I take 509.7 divided by 163.3, I would get 3.12. And what that physically is telling us is if I were to take and apply this force instead of at point A, if I were to apply it about 3.12 feet out, which would be like right here, that the effect of either the entire system of forces we were given originally or this equivalent system of forces at point A, that would also be equivalent to applying a single 184-pound force 62.5 degrees elevated from the horizontal at 3.12 feet out. So hopefully that makes sense to you. The big ideal being, if we kind of did the problem in reverse at the end. If I were to have a single force here acting 3.12 feet out, it's going to induce a couple in the counterclockwise direction. So basically what I did is I determined that distance in order to make the couple equal to the equivalent couple that I computed at point A already. So a little bit confusing, but I hope that makes sense to you. So in terms of just the final answers, so everyone can see, that is what you would be entering in the MyLab. So I hope that made sense. We'll do a three-dimensional example in a minute. I was going to do it in this video too, but this video is already way too long.